Okay, welcome to Module 4. Here we're going to take a look at confidence intervals and hypothesis testing. We're going to start out by talking about confidence intervals around the mean value for normal distributions. And because of the central limit theorem, it turns out that for any underlying population distribution that we have, we can make use of the normal distribution to make predictions about how likely it is that a sample mean is within a certain range of the true population mean. All right, so we're going to take a look at how to compute and how to interpret confidence intervals about the population mean. We're also going to take a look at something called t-scores, which adjusts the confidence interval around our estimate of the mean to take account of the sample size being less than infinite. And we're going to take a look at how to use IL to do these computations. All right, I need to remind you of a couple of things from Module 3 before we press on here. First of all, let's remind ourselves what the what the central limit theorem says. If we select a random sample of n observations from any population, no matter how that population is distributed, then if that population has a true population mean mu and a true population standard deviation sigma, the sampling distributions of the means of all samples of size n is going to itself be approximately normal. That is, even if the underlying population is not normally distributed, if we take some arbitrary number of samples of size n and we look at the distribution of the means of all of those samples of size n, then those samples will be approximately normally distributed, and the mean of the sampling distribution is related to the true population mean by a simple equality. So the mean of our sampling distribution is going to be equal to the mean of the underlying population, even if the underlying population is not distributed normally. Also, the standard deviation, okay, it doesn't seem to want me to be able to highlight this. The standard deviation of the sampling distribution is related to the standard deviation of the underlying population by this equality. The standard deviation of the sampling distribution is the true population standard deviation divided by the square root of the sample size. Now, the central limit theorem does require each sample to be large enough. That is, this value n here needs to be, let's say, 30 or greater in order for us to be able to have confidence that the sampling distribution of the means is normal. But let's assume we've dealt with that. We have selected at least 30 items in our sample. Okay, now let's suppose that we do have a normal distribution with some mean mu and some standard deviation sigma. Then for convenience, both of conversation and talking to other people, and also looking up things in tables and books, it's common for a given value to compute what's called the z-score, which is a standardized way of representing either how far above the mean that particular value is or how far below the mean that value is in terms of multiples of the standard deviation. All right? That is, we take some arbitrary normal distribution. In this case, we have a normal distribution with a mean of 5 and a standard deviation of 2. And by doing this simple linear computation, taking whatever our value for x is and subtracting the mean and dividing by the standard deviation, we convert to what's called the standard normal distribution that has a mean of 0 and a standard deviation of 1. And then starting out with some particular value x, like in this case, our particular value is x equals 7, our mean is 5, standard deviation of 2 is 2. If we do that linear conversion, 7 minus 5 divided by 2, the z-score that we get is 1, which tells us that that value of x equal to 7 is 1 standard deviation above the mean. And we can then compute the probability of that particular z-score either being above 0 or, which in this case is, it turns out is 0.34. Or we can compute the probability that any value that we might draw is less than that z-score, which would give us a well, that's what we're going to get to next. Okay, so let me get to that. So the z-score is a normalized way of talking about how far away from the mean a particular data point is or could be based on the standard deviation of that distribution. Now, often we're interested in knowing what is the probability of being within some certain number of distributions of the mean? Okay, so if we take the actual distribution that we have with some mean and some standard deviation and some particular value and compute z-scores, just to normalize things, we discover that 68% of the data approximately is within 1 standard deviation of the mean. 95% of the data approximately is within 2 standard deviations, and a little over 99.7 is within 3 standard deviations. Okay, now these are approximate. Here I've got the IL tool up with a standard normal distribution set up, mean of 0, standard deviation of 1, and it turns out that the probability of some value drawn from this distribution falling within plus or minus 1 standard deviation of the mean is 0.6827. So it's actually a little bit more than 68%. People often just refer to that as a 2/3 probability of being within 1 standard deviation. And then for 95% of the data, plus or minus 2 standard deviations is approximate. So if I want to go out plus or minus 2 standard deviations, notice that that's actually 95.45. The actual closer bounds for obtaining a 95% probability is 1.96. All right, so there is a 95% probability, a 0.95 probability, that we will fall between minus 1.96 and 1.96 from some arbitrary value that we select. And then for 3 standard deviations away, we'll go from minus 3 up to positive 3. And according to IL, it's 99.73. The point is, it's almost all of the data within a normal distribution is contained within 3 standard deviations of the mean. And this is where we got that empirical rule that we talked about during the first week of, if you want to estimate the standard deviation of a distribution, you can compute what you think is a range that will account for almost everyone, and then divide that range by 6, and whatever you get is at least a reasonable initial estimation of what the standard deviation might be. Okay. So, the central limit theorem tells us that if we have a sampling, if we take a sample of a certain size n, and as long as n is large, then the distribution of all such samples will approach a normal distribution. Now, in real life, of course, it's going to be too time-consuming and too expensive to sample a huge number, not nearly to say all possible distributions of some size n, or samples of some size n. What we ideally want is to just take one sample of size n and compute the mean for that particular sample of size n, as well as the standard deviation for that particular sample of size n. And we want to use the x bar that we got for that sample and the standard deviation that we got for that sample to draw conclusions or make estimates about how close we think we are to the true mean of the underlying population. Intuitively, I hope it's pretty clear. I mean, this is what the central limit theorem is telling us. I hope it's pretty clear that if you take a very small sample size, that your mean of that sample is probably not going to be very close to the true mean. If you take a larger mean, if you take a larger sample, then the mean that you get for that sample is more likely to be closer to the true mean. This kind of thing is common in political polls, consumer surveys, pharmaceutical studies to test the effectiveness and possible risks of medications or medical devices. We use the letter C to describe the confidence interval. So the confidence interval, the way we frame this question here, the confidence interval would be 95%. And we use the letter alpha to describe the region outside of the confidence interval. So in this case, in this framing at the top of this slide, we want a 95% confidence interval of a value between two particular values. And then the alpha is just whatever falls outside of that confidence interval. Okay, so here are some other common z-scores that over time, if you do a lot of statistics, you'll just end up memorizing. I don't have all of these memorized, but roughly between plus and minus 2/3 of a standard deviation is where half of your population is going to fall in a normal distribution. 1.96, as we saw, is a 95% range. 2.58 is 99%. And as we saw, 3 is 99.73. So 3 standard deviations accounts for very nearly everybody. And then here are some other intermediate values. 1.645 is another common critical z-score to remember. 90% of your observations from a normal distribution will fall in the range between minus 1.645 standard deviations and plus 1.645, which in this case would mean that the alpha, the probability of being outside of that region would be 10%. Okay, so back to the statement we made a couple slides ago. We've taken one sample of some size n, And presumably, we've chosen an n that's large enough that the central limit theorem can be applied. This sample has a standard distribution of S. We want to draw some conclusion about the unknown population mean. We want to be able to say things like, there's a 95% chance that the true population mean falls between, let's say, x sub 0 and x sub 1. Some x bar sub 0 and x bar sub 1. Some range of possible values. As a very specific example, let's suppose we want to know the average amount of money that a Pittsburgh household spends yearly on internet purchases. Let's suppose that our sample size is 36, so n is 36. And for n being 36, we compute a mean of $350 per year with a standard deviation of $180 per year. Now, this sample is large enough, 36 households, that intuitively we think that the true population mean is likely to be fairly close to $350, the mean of the sample. But it's also very unlikely to be exactly $350. The idea that the population mean would be exactly the same as the sample mean, that's pretty unlikely. Now, we rely on the central limit theorem because our sample size is greater than 30 to compute a confidence interval of how close we think the true population mean is to $350. Okay, so if the true population mean of the population is mu, and the true population standard deviation is sigma, and our sample size is large enough, greater than or equal to 30, then that means that the sample mean, the sampling distribution's mean, is approximately normally distributed with a mean that's the same as the population mean and a standard deviation that is equal to the population standard deviation over the square root of the sample size. Okay. So, we have our question again. Given that we have a sample with a mean of x bar, and that sample standard deviation is S, what can we say to a 95-degree level of confidence that the population mean is within some interval around that x bar? Well, in order to have a 95% confidence interval, we've already described that means we're looking for an interval of plus or minus 1.96 standard deviations around the mean. Okay, so our z-score, z sub 0.95/2, because we're looking at a two-sided tail here. We're looking for values that are close to the mean as opposed to values that are far to the right or far to the left. Then the central limit theorem tells us this: the probability that the sample mean is between the population mean and minus 1.96 standard deviations, or the population mean plus 1.96 standard deviations, that the probability that our sample mean falls within that range of the population mean is 0.95. Well, from there we can take a leap, because this expression here, this equation here, telling us that when we draw a sample, when we draw a large enough sample from the population, that there is a 95% chance that the mean of that sample will fall within 1.96 standard deviations below the population mean and above the population mean, we can rewrite that to say that this means that the population mean, the true mean for the population, is within plus or minus 1.96 standard deviations of the sample mean with a 95% probability. Now, that seems like a very big leap to go from what we accept that the central limit theorem says to making this claim that we can actually just take one sample of size n from the underlying population, and with a 95% confidence level, we can claim that the true population mean is within plus or minus 1.96 standard deviations of that sample mean. But it turns out that getting from this central limit theorem statement to this analogous statement that tells us about the probability of being close to the true mean is just a matter of algebra. So you don't need to remember this, but I just want to show you that this isn't just pulled out of thin air. So let me actually do the algebra for you. Okay, so I don't want to carry all of this notational mess around. Let me simplify things a little bit. We have the statement that the probability of the mean minus some interval, I'm going to call it A, is less than or equal to the sample mean, which in turn is less than or equal to the true population mean plus that same interval. That probability is 0.95. Okay, so this is what we start with from the central limit theorem. There's a 95% probability that when we draw a sample from this population, that the sample will fall within this interval, population mean minus 1.96 standard deviations and population mean plus 1.96 standard deviations. Now, I claim it's just algebra to get from this step down to the next step. Let's see if that's true. So the probability that this first equation, this first expression is equal to 0.95 means that minus a is less than or equal to x bar minus mu, which in turn is less than or equal to a. All we've done here is to subtract mu from all three sides here. If we subtract the same value from all three parts of this expression, then minus a is less than or equal to x minus mu, which in turn is less than or equal to a. So that's also going to be 0.95. Well, next step is let's just subtract x bar. So minus x bar minus a is less than or equal to minus mu, which is less than or equal to minus x bar plus a. That's equal to 0.95. Well, as the final step here, we just multiply this expression through by minus 1, and that has the effect of switching the inequalities. Let me just persuade you that that's true. If m is less than n, which is less than p, then I think you'll believe me that minus m has to be greater than minus n, which has to be greater than minus p. Okay, so if we multiply through by -1, the signs switch around, the inequalities switch around. So that means that the probability of x bar plus a is greater than or equal to mu, which is greater than or equal to x bar minus a, is 0.95. And then we just, move the inequalities around again and just switch the sides of things. This is the same as x bar minus a is less than or equal to mu, which is less than or equal to x bar plus a. You don't need to remember any of that. But I just wanted to show you that it's not just made up. That this statement, mu minus 1.96 times the standard deviation, being less than or equal to x bar, being less than or equal to mu plus 1.96 times the standard deviation, if that probability is 0.95, then this probability is also 0.95 just by algebra, even though we've only drawn one sample of size n here. We can make this claim about how close the population mean is to that particular sample mean that we drew. All right, so that is critically important. Okay, so now that we've demonstrated that these two probability equations are just algebraically the same as each other, I do want to point out that we're making an approximation here that the population standard deviation over the square root of n is approximately the same as the sample standard deviation over the square root of n. That is only an estimate, only an approximation. We need to know about what are called t-scores in order to make this exactly correct. But for the moment, just to follow through the whole process of figuring out how to compute confidence intervals, we're going to pretend that we can use the sample standard deviation as an approximation of the population standard deviation. All right. And so this justifies us in concluding that there's a 95% chance that, not m, mu, the population mean, is within 1.96 standard deviations of the sample mean. So coming back to our specific question, we have a sample of 36 households. From that sample, we discover that these households are buying a mean of $350 of stuff from the internet with a standard deviation of 180. And so we want a 95% confidence interval, so we use our z-score of 1.96. Our error bound is therefore 1.96 times the population standard deviation, which is the sample standard deviation over the square root of n, blah, blah, blah. And we grind that out. I'm not going to step through things piece by piece. And we conclude that that there's a 95% probability that the true population mean of internet purchases is $350 plus or minus $58.8. Okay, so in other words, there's a 95% chance that the true mean of internet purchases is between $291.20 or $408.80. All right, so let's take a look at using the aisle critical value widget and take a look at how to compute confidence intervals using aisle. I'll go back to my collection of widgets. And, okay, so I've got data sets, I've got widgets. Here's my critical value widget. I pop that open. And, all right, we want a 95% confidence interval. And recall that alpha is the probability of being outside of the confidence interval. Since we are using a two-sided tail, that is, we are wanting to be close to the mean, but if we're not close to the mean, we don't care whether we're too high or too low. And this is where we got our 1.96 z-score from. Then we will go to our normal distribution and figure out that if we have a mean of, well, let me go back and check what that was. Okay, so the mean was $350. So the mean is $350. The standard deviation from our sample is $180, but it's divided by the square root of n. So $180 divided by square root of 36, $180 divided by 6 is going to be $30. And 1.96 times $30 is where we get the 58.8 from. So if I go 58.8 below the 350, that's where we get the 291.2. And 58 above 350 is going to be 408.8. And indeed, all right, so plugging those values, 350 for the mean, 30 for the standard deviation, and using our 1.96 times the standard deviation of 30, we see that there is a 95% chance, according to the central limit theorem, that the true population mean is between those two values. Now, if we dramatically increased the number of households from 36 to 10,000, that would reduce the bounds of our error. That would reduce the standard error of the mean significantly. So suppose that we did go out and sample 10,000 households, and in this 10,000 household sample, purely by luck, we got the same sample mean, and purely by luck, we got the same standard deviation. Now, that's vanishingly unlikely. Even if we took samples of size 36 over and over and over again, it would be very unusual for two samples of size 36 to have the same sample mean and the same sample standard deviation. So the likelihood of this happening if we take a different sized sample is tiny. But let's suppose that, we do take a sample of 10,000 households. We do get the same sample mean and the same sample standard deviation for that particular sample. Then, because the sample size is so dramatically large, that means that when we compute our standard error of the mean, it's going to be a lot narrower. It's going to be 180 divided by 100 instead of 180 divided by 6, and we get a much narrower 95% confidence interval around our mean. So now we would say that there is a 95% chance the true population mean falls between 350 minus 3.53 and 350 plus 3.53. Right? So collecting more data is a good idea. It gives you a much narrower arrow bound, and in other words, a tighter confidence interval. what if we wanted to be more confident? What if we now this is going to sound backwards. What if we wanted a 99% confidence interval around the mean? Well, we can get a 99% confidence interval around the mean by increasing z from 1.96 for 95% up to 2.58 for 99%. Okay, and we can get that from the critical values tool. All right, so let's suppose that we decrease the alpha outside of our confidence interval to 0.1, and we see that now we have the two-tailed z is 2.5758, so 2.58. And the downside of getting this 99% confidence interval with the same sample size as before and the same mean and standard deviation that we got before is we do now have a 99% confidence interval, but it's actually wider than the 95% confidence interval that we had before. So the cost of increasing our confidence, everything else being the same, is that our interval widens. Take this to the extreme. What if we wanted to be 99.99999% confident that our interval contained the true mean value of internet purchases? Well, ultimately, we could say, well, an interval from 0 to 5,000, let's say, we can be hugely confident that the true mean of internet purchases is between 0 and 5,000. But of what value is that information, even though we're enormously confident that that information is correct? There's not much we can do with a confidence interval that's so wide. So it's always a trade-off between how confident do you need to be versus how much data do you need to obtain, and what is it going to cost you to obtain that data? Okay, so to summarize, if we take a sample that's large enough that we can rely on the central limit theorem, then the error bound around our sample mean, in which we have some level of confidence that the true mean actually falls, is going to be given by the z-score for the confidence level that we want, times the population standard deviation divided by the square root of our sample size. And the narrower we can make that error bound, for a given level of confidence, let's say, the better information we have, the better knowledge we have of what the true mean actually is. Now, in this equation, for computing our error bound, if we want to make that error bound smaller, there's only two possible things we can adjust. We can adjust the z-score, the confidence level, or we can adjust n, the sample size. Since sigma is the standard deviation of the population, that's just a number that can't be changed. We want to try to measure it accurately, but it's not a number that we can change. So if our sample size is fixed and we want to increase or we want to have our error bound decrease in size, we can only do that by decreasing our level of confidence. Okay, this is this ridiculous example that I gave of, being 99.99999% confident that the average internet spending is between $0 and $5,000. Okay, so you're really confident, but that totally blows up your error bound and makes it essentially useless information for making any kind of decision. The other way that we can reduce the error bound while leaving our confidence interval, our z-score, the same, is by increasing the size of our sample. We can go out and gather more data, okay, and that will decrease the error bound by the square root of the amount of data that we get, and that was illustrated up here, where we increased our sample size to 10,000 households instead of just 36, and that very tightly narrowed the error bound of our 95% estimate for the true mean. Okay, so often we have dictated to us the required level of confidence and the required narrowness of the error bounds. All right, either our customer or our boss or maybe a government agency or regulation, in order to provide appropriate information for some manager or somebody to make an appropriate decision, you might be required to have a 95% confidence level in your estimate of the mean, and maybe you're also required that the error bounds on the estimate are plus or minus $5 at most. Okay? Well, so now the question is, given that the error bound is fixed and the confidence level is fixed, the only thing that we can actually change then is the sample size. And so we can flip around our equation for the error bound here, multiply both sides times the square root of n and divide by the width, and then square. So in our case, if we want a 95% confidence level, we know that the z-score we're going to need is 1.96 for that. We divide by the width of our interval and multiply by some estimate of the population standard deviation. Here we're using our original sample's standard deviation, which is suspect, and I'll address that in a minute. And we can simply run this computation and get told that, all right, if we want to maintain a 95% confidence interval level of confidence in our interval around the true mean, we're going to have to crank up our sample size to approximately 5,000 in order to get that narrow an error range. All right. Now, I said that using this previous sample's standard deviation is suspect for backing out what value of n we should be using. To compensate for the fact that this value of s is suspect, instead of using ordinary z-scores when we do our computation here and when we create our confidence intervals, what we're going to use instead is something called t-scores. Okay, t-scores take account of the fact that our sample standard deviation, just like x bar, is a sample statistic. And if our sample size is low, that implies that our estimate of the population standard deviation by using the sample standard deviation is likely to be a poor estimate. The more data we collect, the closer to the true population standard deviation our sample standard deviation is likely to get. So the t-score depends on something called the degrees of freedom in the context of doing these computations. And basically the number of degrees of freedom is a measure of how much data you have minus the number of statistics that you've already created or calculated from the data. And so the t-score, in order to get the t-score, we have to have already computed our estimate of the sample mean. That means we have sort of burned the data once, we've analyzed the data once in order to get our estimate of the sample, in order to get the sample mean, our estimate of the population mean. And so the t-score is driven by the number of data in our sample, n, minus the fact that we've already computed one statistics. And here is a table of the t-scores that we should be using in preference to the z-scores, particularly when we're dealing with small sample sizes. Okay, so this is a screenshot from some book. If you have a really small sample, so that your degrees of freedom is 1, what that literally implies is that you took two, you measured two observations, you computed your mean as the average of those two observations, and then to compute the sample standard deviation, you had to divide by, remember, you had to divide by n minus 1, which is 2 minus 1, which is 1. And so your standard deviation is going to be very broad. Your sample standard deviation is going to be very broad. And consequently, the t-score, I guess I can't highlight that, the t-score corresponding to a certain level of confidence is also going to be much larger than the z-score for that same level of confidence. All right, this table is for a one-sided tail. If we're interested in measuring an estimate, in providing an estimate for the population mean, that means we want to be close to the population mean, which means that we have a two-tailed distribution. And so for a 95% confidence level, two sides would be double this 0.025 level. Okay? All right, so let me show you the t-value for the t-distribution critical values. Here's our critical value tool over here. We want, as before, a 95% level of confidence. Our degrees of freedom, well, 1 is kind of absurd, but let's use, remember our original sample was 36 households, and therefore our degrees of freedom after we've calculated the mean of that sample is going to be 36 minus 1, which is 35. Okay? And so according to the t-distribution, since our estimate of the standard distribution, our estimate of the standard deviation of the sample is not reliably perfectly normal, what the t-distribution is telling me is instead of using the z-score of 1.96 to create my error bounds, I should instead use this adjusted t-score value of 2.0301. Okay, and so here's a similar example, this time just to make the computation a little easier. We're going to assume that our sample size is 16. All right? So we've taken a sample of 16 households. We have computed that the sample mean of the amount of internet purchases is $350. The sample standard deviation from this sample is $180. And so we're going to conclude with a 95% level of confidence that the true mean, okay, the true mean for the amount of money spent by an average household falls between the sample mean, okay, didn't highlight that second one. All right, the sample mean minus or plus the t-score corresponding to our sample standard deviation divided by the square root of n. All right, so our sample standard deviation okay, we're reading it off the page here is 2.13. This table is showing the two-sided probabilities. Let me put in our, okay, so our sample size this time is 16, which means our degrees of freedom is going to be 15. And so our two-sided t-score is 2.1314, all right, 2.131. So we're going to say that we are 95% confident, which is to say we have an alpha of 5, 1 minus 95%, that the true mean for internet expenditures per household is the sample mean plus or minus the t-score times 180 divided by the square root of the sample size. In this case, that's 180 divided by 4. So 16 square root is 4. And that gives us this range. Okay? 254.10 to 445.90. Let's compare that. Okay, so 254.10, 445.90, whereas before, where we had a sample size of 36, and we decided inappropriately that the sample standard deviation could be directly used as a substitute for the population standard deviation. So based on z-scores here, our 95% interval was between 291 and 408. All right, so 291 and 408 versus 254 and 445. So the better 95% confidence intervals using t-scores rather than z-scores is from 254.10 to 445.90. All right. So in reality, you should always be using t-scores because you never, well, I say never, but of course we saw one example of water usage where we did know the entire population data, but it's very, very, very rare in reality that you have entire population data. You are usually trying to estimate the population mean from a sample of some size. And for doing that, you should use the t-score rather than the z-score. Notice, however, that as the sample size gets larger and larger and larger, the t-scores get closer and closer and closer to the z-scores. Okay? So for a two-tailed t-score, if our sample size is 100, our t-score is 1.984 as compared with the z-score that the t-scores converge to of 1.96. Okay, so often this is why if you look at tables and books, the t-scores are only shown out to a degree of freedom of 100, because beyond 100, you might as well just use the z-scores anyway, because you're converging to the z-scores pretty quickly. Okay, so this slide kind of repeats what I just said. We don't know the population mean almost ever. And we have to use, we don't know the population standard deviation almost ever. We are therefore stuck with using the sample standard deviation as an estimate of the population standard deviation. But because we are less sure about how close that sample standard deviation really is to the population standard deviation, we use t-scores rather than z-scores. Sorry. We use t-scores. Runaway mouse. All right. We use t-scores rather than z-scores when we compute our confidence intervals. Now, as n gets larger, the t-scores converge to the z-scores. And here we're suggesting that once the sample size has gotten to 30 or more, the t-scores are not particularly different from the z-scores, and you can get away with using the z-scores. Now, okay, I'm gonna say two things about that. First thing, you should always use the t-scores. The t-scores are the correct thing to use. This cutoff of 30 is conventional. It's kind of what's widely used. I don't personally feel comfortable that, and of course the table doesn't even show it in here. This table doesn't show it. This table doesn't either. This only goes up to 20. Unless collecting data is enormously expensive, I think you're a lot better off just assuming that you ought to be using 100 as your kind of minimum safe sample size if you want to just use z-scores rather than t-scores. My opinion. You can ignore me. Okay. So the real problem with using small sample size is that if we use a small sample size, then we can't rely on the distribution of the sample means to have converged to a normal distribution under the central limit theorem. Okay, so it is important to use a sample size of at least 30, both so that the central limit theorem can be relied upon, and so that if you want to use z-scores rather than t-scores, you can kind of get away with it. But I would suggest using t-scores anyway. And I would suggest using a minimum sample size closer to 100, unless it's really expensive to collect data. Let's do an example with ISLE to see how we can compute a confidence interval now that we know about t-scores. Okay, so I'm going to do the first of these two tests of understanding. For the following sample statistics, mean is 2.0, standard deviation is 0.75. Okay, this is the sample mean and the sample standard deviation. N equals 36. By hand, compute a 98% confidence interval. Okay. Well, I'm going to interpret by hand there to mean that we can use ISLE to help us along. So, the first thing that we need to do is figure out what our critical value is. This is a sample of size 36. It's well less than 100. It's just a little bigger than 30. And so I am going to be a good citizen and use the t-distribution instead of the normal distribution to figure out my confidence interval. We want a 98% confidence interval, which means that my alpha is going to be 0.02. My sample size is 36, which means that my degrees of freedom is 36 minus 1 is 35. And therefore, my two-sided critical value for t is 2.4377. All right, so 2.4377. Then we're going to go to our normal distribution. And let's see, I need to refresh this so that I can see come on now, I need to see the available tests. We want this test. We want a 98% confidence interval. Our mean is 2. Our sample mean, our sample standard deviation is 0.75. And we want 2.4377. I guess here's where the by hand part comes in. Let me switch to my document camera. Okay. So we're going to have our error bounds be the t-distribution, alpha over 2, so that's going to be 0.01 with 35 degrees of freedom times the sample standard deviation over the square root of the sample size. And that's going to be, let me get that t-score back. Okay, so that t-score is going to be 2.4377. S is 0.75. Square root of n is 6. Let's see. 0.75 divided by 6 is conveniently 0.145, I believe. Is that right? So by 6. Well, we'll pretend. And we want 2.4377 times that. Let me fire up a calculator so that I know I'm doing the correct thing here. I don't know if you can see my entire calculator, but 0.75 divided by 6. 1.25. Well, that's obvious, right? 0.125. And then that times 2.4377, 2.4377 is 0.3047. Okay, so there's our error bound. So what that means is the probability of falling within, okay, so the mean is 2, so we've got 2 plus or minus 0.3047. So 2.3047 is our upper bound. 1 point, oh, can I do this? 6953. 6953. 3047. I think I did that correctly. So what is the probability of falling within this range? Well, supposedly the probability should be 99%. Let's see what we get. Actually, no, this is the normal distribution. All right, we're looking at the normal distribution tool here. So we're going to end up getting a value that's greater than 99%. We're going to go from 1.6953 to 2.3047. And, oh, I see. I did the standard deviation incorrectly. This should be 0.125. There we go. All right. And so it's approximately 98%. Probably just a little higher than that because I'm using the normal distribution tool rather than a t-distribution tool. Okay.